What is calculus? Calculus by Daniela Spina. So calculus is the study of how things change. It provides a framework or modeling systems in which there is a change, and we have a way to deduce it with the predictions of such models. It just provides a way to construct relatively simple quantitative models of change instead of going to complex models where the change is not so notorious. So once we know the importance of what is calculus, we can start seeing some of its divisions. Its main divisions would be derivatives, integration, and we have some kinematics here, which are also relevant to the topic. So we have integration, derivatives, and kinematics. Let's start with derivatives. So what is a derivative? This is the first principle. The first principle is just a way to define derivative in a mathematical way. So we know the limit as h approaches 0 is the f of x plus h minus f of x and h. This expression I just showed you here comes from the y1 minus y over x1 minus x in a graph where we have instead of x and y, x plus h and f of x. So basically it's just a way to show what is a derivative in a mathematical way. Now once we know the mathematical definition of a derivative, we can go here. We have some primitive derivatives, which are derivatives that are stated and will always be this way. So these are some of the primitive derivatives. We have sine x, cos x, sin x equals cos x equals negative sine x, xn, x to the power of n equals n times x to the power of n minus 1, ln x would equal 1 over x, and overall ex equals ex. Now what if we have e to the power of a function? Well, it would be e to the power of a function times the derivative of that function. ln2 times a function will be 1 over fx times the derivative of the function. And a function to the power of n will be n times the function to the power of n minus 1 times the derivative of that function. So now we can go and do an exercise here, a very quick exercise. But first we need to see this. So if we have a function, we need to identify the outermost function, derive it, keep the innermost function the same, times the derivation, identify the other outermost function. So after you derive the first part, you keep everything equal. Then now you derive the g, which is the second most outermost function, if I make myself clear. So derive that and keep the inner part the same. Then derive the other inner part would be h, and then finally derive k. So this rule just tells us basically derive from the outside to the inside. So let's do an exercise here. Alright, so what if they give us f of x equals sine cos ln x? So first with this idea, we will derive the initial part, which is sine. So let's derive it, cos ln x. Now we need to multiply this times the derivation of the second part, which will be negative sine ln x, times the derivation of this part, which would be 1 over x. So this would basically follow the rule that j h k would equal g1 h k times h1k times k1. It's just doing that basically. Now let's continue with our derivative explanation here. Now once we know how the primitives and the extensions work, we can go ahead and see something more advanced. So we have the rules, some rules. A product rule, uv equals uv1 plus vu1. This means u times the derivation of v plus v times the derivation of u. So this u and v are just parts of the formula we are given, and we need to know when to divide the function into two parts and do this process. This quotient rule follows the same principle, but of having two parts of the function that are being divided, and when you identify those two parts, you can state v times the derivation of u minus u times the derivation of v divided v squared will give us the quotient rule. It's just a way to make things easier. The chain rule is a rule that is useful in many formulas. It just says when you have more than one function, so a function that is doing something to another function, you go from the outside layer to the inner one. This is just what we explained, and here I have an exercise that can help us understand it. So sine times cos times ln x is the exercise it did there, and as you can see, this is our result. We go from the outside to the inner layer. Now what if we have, this is not a negative, this is just stating the other point. So u plus v equals derivation of u plus derivation of u of v, sorry, and u minus v would equal derivative of u minus derivative of v. So it's a very straightforward derivation formula. Now we have something that is very important for derivation and helps us deal with real life problems. This is optimization. It's a way to use derivation in real life exercises to find the mean, to find the max. Suppose you have a farm and want to know what is the maximum area. Well, this can help you. Optimization has three basic parts: the first derivative test, the second derivative test, and the inflection point test. The first derivative test is simply saying the derivative of the function of x equal to 0 will give me a critical point. In this case, we have x, suppose this is y, equals x. So the function of x will give us an x value. That's better. So now in this case, the function of x gave us a 0 value. This 0 value will be known as our critical point. If x equals 0 and x equals c, then c equals 0. That's basically saying that. When we do the first derivative test, we will get a max or a min, a critical point. Well, when we do our second derivative test, for example, f second derivative of x equals a negative number, then it is a max. They have an inverse relation. This is an inverse relation, and if it's a positive, it would be a min. This is a part of the derivative. For example, if we get f11x equals 2, we know this has an invisible positive sign and thus would be a min. Now we have the inflection point test. This is a test when we equal our second derivative to 0, we will get an inflection point. Now they are just subjects. These are just probabilities of it being an inflection point. To know for real if what we have is an inflection point, we need to do the following. So we get a value. In this case, let's say 0. So we choose a value slightly smaller, a value slightly bigger, and then say f11 negative 1. You see, replace the smaller value, the slightly smaller value, into the function you have. If after doing this you change from a negative sign we see here to a positive number, then that will mean we have half of the progress done. Then we need to second derivate the slightly bigger value, and we need to get a change of sign. If we get a change of sign in both of our subjects, then we know 0 is an inflection point. This is just a way to be for sure if you are getting the max value. The inflection point value. Because functions in calculus are just subjects to change. You have subjects to change and you want to analyze whether the subjects are correct or not. So these tests are very useful with real life exercises, and that shows us the importance of calculus. Now let's go to integration. So integration first, let's define it as the opposite of derivation. When we integrate something in maths, usually it's done to find the area under a curve, but it has many more applications. It can help us do the inverse application of derivation. So we have indefinite integrals and definite integrals. An indefinite integral is one which doesn't state from which point to which point we are going to operate the curve, and this one does tell us. So here we will have any real number. For example, we can have 1 and 0, -1 and 20. It can be a very broad range of values. As in derivation, it also has some primitive values. So x to the power of n dx, you need to put dx always. It helps us know in respect to what are we integrating. So it would be x to the power of n plus 1 over n plus 1. And if you notice we derivate this, it will equal the derivative. So if we derivate this, we will get, if we derivate this, we will get this value again. Okay, so now we have sine x dx would be negative cos x, because we are working with the opposite of derivatives, remember. So I forgot to tell you, these plus c's can be any number. It is a way for maths to avoiding any mistakes. By this I mean sometimes you could get a left result you don't stay here. So if we only write this, it could be potentially wrong, as we are leaving a part of something out, and this is what the plus c does for us. It avoids any mistakes. The integration of cos x will be sine x plus c. E to the power of x dx would be e to the power of x plus c, and 1 over x dx equals ln x plus c. Here we don't work with ln x on standard level, but we do work with 1 over x. So here are some rules. The integration of k times f is the same as the constant out. So this is a rule that tells us we can always bring our constant outside the derivation. Integration of f plus g is integral of f plus integral of b. Integral of f minus g is integration of f minus integral of g. They are exactly the same. Here we are saying, remember that the function of x dx is the same as a function of u du, and is the same as a function of s d. So basically, just saying they are equal to avoid confusions. Now this is the fundamental theorem of calculus. The derivative, a definite integral, here we have a and b, fx dx, would be the big f of x b, which would be this value here, we plug it in here, minus big f of x a, which would be this value. And this is many times used to get the area under the curve, as it will subtract two parts of a function, giving us a clear area on which to work with. Use substitution is a way of simplifying integrations. For example, here we have a complex, well, this one is not that complex, we could do it without use substitution, but it's a lot easier with use substitution. So the steps are the following. First, find something that its derivative is primitive. If you can't find it, just find something that is, usually this helps, that is being influenced by something else. For example, here we are being influenced by the power of 7, so this just gives us a clue of what it would be our u in this case. So let's say u will be equal x to the power of 3 plus 5. In this case we do it because we know the derivative of this can help us get this and this at the same time. So the derivative of u with respect to x would equal 3x squared, then du equals 3x squared dx. As you notice, we just got that 3x squared dx would be u du, so we can say this with this is du. And now let's replace this as being our u and this as being our du. So once we do that, we get u to the power of 7 du equals, we follow the rules. Now we're going to try and integrate once we have our function in terms of u and du. After we do the integration, we must replace the values with the original value. The du disappears. Once we integrate, this goes out. So that's why we don't see it anymore here. And instead we see a plus c to avoid any errors, as mentioned before. So x3 plus 5 to the power of 8 divided over 8 plus c would be our integration of this initial problem. Now let's go with kinematics. This is just a way to use derivatives and integration on real life. What happens if we derive displacement? We get velocity. The second derivative of displacement will give us acceleration. The derivative of velocity will give us acceleration. Now the integration of acceleration will give us velocity, and the integration of velocity will give us displacement. We can also say as second derivative would equal acceleration, velocity first derivative would equal acceleration. The integration of a will give us v, and the derivation of v will give us s. So we first derive acceleration, and if you want to find displacement, you gotta first integrate acceleration, then integrate velocity, and you can get your displacement. So I hope this helps. It was a video, I think it will be very useful for me. It just brings in the basic concepts of derivation and integration. And that's it. Thank you.